Okay, so welcome to section 2.1, inductive reasoning and conjecture. This is the introduction to this chapter is to the part where people struggle with the most in geometry, which is the proof-based portion of it. So we're kind of setting some foundations for some skills we're going to use later on, really for the rest of the year. So this may not feel like math, even though we're using math terms and stuff. It might feel more like an English class, and it kind of feels like that for a while. So just kind of, hang on, and hopefully this makes sense. So here we go. First thing, conjectures. Well, and you're gonna maybe want to pause this and then copy it, or if you got your textbook next to you, you can copy out of there. But the first thing I ask you is to define inductive reasoning and conjecture. So inductive reasoning. Now, what inductive reasoning is its reasoning uses a specific number of examples to arrive at a conclusion. Okay, so you look at a few examples, you arrive to a specific conclusion. Basically, you're observing a pattern. Okay, and so when you're using that pattern, you're kind of predicting what's going to happen next. Now, the next definition is conjecture, and that's the conclusion, or they use concluding statement you use using inductive reasoning. Okay, so for the first example here, just right out of the textbook, it's write a conjecture and then use your conjecture to find the next item in the sequence. So, for instance, there's a movie showing at 8:30, then at 9:45, then 11 a.m., then 12:15. So the first thing you would do is look to see is there a pattern, and hopefully it's pretty obvious that every hour and 15 minutes this movie's playing. So that's your pattern. Your conjecture is the show is an hour and 15 minutes greater than the previous one, so every hour and 15 minutes we have a show. Now your next term then would be, okay, take 12:15 and add an hour 15 to it, 1:30 p.m. Okay, so that's how inductive reasoning works. And to be honest, that's how most things work in real life. We just use patterns. And any of you that are big video game fans, that's what you're basically looking for when you're playing a video game. What's the pattern? What's going to happen next? And you keep trying to, get to the next step. And so our brains are pretty naturally tuned to do inductive reasoning. Okay. Another example here, a little more geometric than the previous one. You got a drawing. So you've got this box, and then you keep putting levels around it, like backwards L shapes around it. And the question is, okay, if I use this to make toothpicks or segments in this case, but you could do this with toothpicks, how many would I have for the next figure? Well, at first I have 4, then I have 10, then I have 18, then I have 28, then I have 24. So I'm adding 6, 8, 10, 12. So it's saying it's increasing by 6, 8, 10, 12. How you actually describe that is you're adding consecutive even numbers. So the next one we assume to be, if it's 6, 8, 10, 12, we'd assume it to be 14. So, okay, we think we'll have 14 plus 40, which would then give us 54 segments. Now to check our conjecture and our conclusion, we could just, sketch it out and take a look, which the book already did for us, and yeah, there are 54 there. Okay. So most of the homework in this section, most of the ideas in this section are looking for patterns that are inductive and then take that next step to get from the conjecture to the next conclusion. So first example, okay, you'll have to, some of these you'll go with the Google Forms to fill this out to make sure you're paying attention to example 1. So write a conjecture that describes the pattern in the sequence, then use your conjecture to find the next item in the sequence. Okay. So looking at this problem, hopefully it jumps out at you. If it doesn't, that's fine. That's what I'm here for. But hopefully you catch that the 1 is the one that might throw you off the most, just the regular 1. But that's really 1 over 1. And that 1 over 4 is really 1 over 2 squared. And 1 over 9 is really 1 over 3 squared. And 1 over 16 is 1 over 4 squared. 1 over 5 is 1 over 5 squared. And if you go back to that 1 squared is 1. So what we're doing is we're squaring the denominator, the next number. So we should have 1 over 6 squared, which is 1 over 36. Is that one of our possibilities? Yeah. Okay. So that would be our kind of number sense 1. Another example. Okay. Again, doing drawings here, checking to see if notice a pattern. So for example 2, write a conjecture that describes the pattern in the sequence, then use your conjecture to find the next item in the sequence. Okay. Oops, wrong button. So next patterns, here we go. So first we have 1, then we have 3, then 6, then 10. So hopefully what you catch is that, oh, I had 1 and then I added 2 on here, and I took the previous figure, added 3, then I took that and added 4. So I'm just adding 1 plus 2 plus 3 plus 4, which gives me the 10 that I have here. So to get the next one, I'd have to add 5. So I have 10 plus 5, which would give me then 15 circles, which is B. Okay. All right, another quick example. Okay. Make a conjecture about the sum of an odd number and an even number. List some examples that support your conclusion. Okay. So the first thing we would do here is just, pick an odd and an even. So I'm going to say O for odd, E for even, and then S for sum. Okay. So 3, 5, 7, 21, 9, I'm just making them up, 2, 4, 6, 8, 10, let's say. So 3 plus 2 is 5. Okay. 5 plus 4 is 9. 7 plus 6 is 13. 21 plus 8 is 29. 9 plus 10 is 19. So I'm looking for a pattern here with this when I add an even and an odd. Okay, so that's my conjecture. So what would I say my conjecture is? Well, hopefully you've caught that all of these are also odd. Okay, so the sum of an even and an odd is odd. And we've seen that it's supported out. You can actually prove this using algebra and factoring, but we're just looking at conjectures and stuff. But that actually is always true. It always will be odd. Okay. And example 4. Okay. Example 4. For points L, M, and N, Lm equals 20, Mn equals 6, and Ln equals 14. Make a conjecture and draw a figure to illustrate your conjecture. Now this one is tough if it just doesn't jump out at you instantly. This is one that, again, through experience, I instantly knew, oh, okay, this is what I'm going to do. But a lot of you probably won't quite catch that. So here's what we have. We have 3 points and 3 segments. That's what we have. So there's one of two things that can happen. And notice it's LM, MN, LN. Okay. So I'm going to draw 3 points. Okay. Now those 3 points can be broken off like this and make 2 segments that just kind of make like a V shape. I could also draw this third side in here, but I'm not going to need that. But maybe we will. Or it could be 3 points that line up and make a big segment. Okay. Now that's the 2 things that can happen. And to be honest, that should be, I wouldn't say it should be a natural thought, but that would be your kind of plan of attacks. Okay, either they line up and they make a line together like a full segment, or they don't, they make like a V shape or like a triangle maybe. Okay. Now, here's what jumped out to me when I looked at this. I said, oh, Lm is 20, Mn is 6, Ln is 14. 26 and 14 should hopefully jump out to you because 6 plus 14 is 20. Which what that hopefully would say to you then is, oh, this is 20, this is 6, this is 14. And now I can fill in some values. I could say, oh, well, what's 14? That is Ln. What's 6? It's Mn. Well, that's kind of weird because we put N on the left and M on the right, but that's okay. And then what's 20? Lm. So what this means for us, and it's what we talked about last chapter, and we'll bring it up again in some later sections in this one, is they have to line up and make a full segment together. Because if they didn't, their lengths wouldn't add up. And I know that Lm and Mn share the point of M. So that's the thing. If this were, if this were L, N, M, this would be weird because this would be 14, this would be 6, this would be 20, and that's more than 20 because it kind of gaps out. So our conjecture is that they line up in a segment, or technically they are co-linear. And that's something we haven't talked about for, at least in this way since the beginning of chapter 1. It does come back in chapter 2 though, and this is one of the trickier examples. So example 4. Okay, now the last little bit of this video, which I'm going to leave you with here, and this is where we're going to pick up in class tomorrow, is counterexample. Now, we've made conjectures, and the ones we've done have kind of worked out nicely. They don't always do that. So for this part here, it's to find a counterexample. This is a false statement, and it can be a number, it can be a drawing, it can be anything. So to show that a conjecture is true for all cases, you have to prove it, and that's hard to do, and that's what we're going to do throughout the rest of the year, really. But this is a key thing here. It only takes one false example to show that something is not true. So if you can find one example that breaks it, you know the statement's not true for everything. And this false statement's called a counterexample. And again, it's a definition you got to copy down. So from the book, you know, the question here is, hey, if n is a real number, which just basically means it's any number you've worked with, if you square it, it's bigger than the number. Now this works for something like, say, 2, because 2 squared is 4, and that's bigger than 2, because 4 is bigger than 2. However, this doesn't work if the number's 1, because 1 squared is 1, and 1's not bigger than 1, 1's equal to 1. It also doesn't work if if this number is less than 1 as well, like 0. 0 squared is not bigger than 0, or 1/2 squared is 1/4, so it doesn't work out that way. On B, if j, k, and kl are equal, then k is the midpoint. Well, in that last example you saw back here, the segment worked out that way, that if they had been 10 and 10, it would have had to have been kind of a midpoint. But here's the deal. If it's an isosceles triangle, we know j, k, and kl would be equal, but they would not be making this the midpoint. So this is kind of a tougher one, because you can see in the drawing where it doesn't work, but if it did, where if k were right on here, it'd have to be the midpoint. So if it's on the same segment, yes. If it's not on the same segment, no. Okay. So for homework for tomorrow, just 4a and 4b, just a couple of quick questions. On the bottom of your notes or on the back there, if n is a real number, then n is a negative number. So find a counterexample to this. Okay. Same thing for B. If ABC and DBE are congruent, then they must be vertical angles. One of our properties from last chapter is that vertical angles are all congruent. In this case, is this true? Okay. So I leave you with that. Again, if you have any questions at all, come in the morning. Probably take us a whole 3 minutes to sort it out. So I'll see you tomorrow.